So in this lesson, what we want to do is we want to take what we have learned thus far about calculus and use it to actually apply it to answer some questions. And basically, the kinds of questions we're going to answer here are we are going to be given some definite and some indefinite integrals, and we want to evaluate these things. And of course, the thing that we are going to use to evaluate these things is the fundamental theorem of calculus. Which tells us that if we want to evaluate the integral of f at x from a to b over dx, we are going to evaluate the antiderivatives at the endpoints and subtract them. Where once again, capital F at x is the antiderivative of little f at x. So let's actually get to an individual question here. It says up at the top here, recall the fundamental theorem of calculus. That's just what we did on the previous slide. So now we want to actually evaluate the following integrals. Now these integrals that we see right here are what we call definite integrals, because we are given definite values of a and b that we want to integrate in between. Okay? So our first one here is pretty straightforward. It is the integral from -1 to 2 of x cubed. And the variable that we're integrating over is going to be x. That's what the dx is telling us at the end. So kind of like in differential calculus where we said we wanted to differentiate with respect to x, here we are integrating with respect to x. Excuse me. Well, first thing we want to be able to do, first thing we're going to need is what is the antiderivative of our function? Our function is f at x equals x cubed. What is the antiderivative of f at x, capital F at x? If we do the antiderivative of x cubed, what are we going to get here? Hey, Yoon? X to the power 4. Okay, so the fundamental theorem of calculus tells us that to evaluate this integral, we are going to take our antiderivative, okay? We are going to evaluate it at the endpoints, so 2, the upper endpoint, and we're going to subtract the antiderivative evaluated at -1, or our smaller endpoint. So it's antiderivative at our endpoint minus antiderivative at our starting point. Why isn't there a c? Because this is a definite integral. Okay? Let's think about it like this. What if we did this in the general case? Okay? Okay, so, oh, no, I don't need to change that. Okay, so if we do our general antiderivative here, 1/4 x to the 4th plus c, let's evaluate it at 2 here. 1/4 2 to the power of 4 plus c minus 1/4 -1 to the power of 4 plus c. So these are our two antiderivatives here. Oh, and I should use maybe round brackets for both of them. Maybe I can try to square these brackets off here just to make it a little neater. Okay. What happens to the c's? They're going to cancel out, okay? So I was actually a step ahead of myself, and I was getting rid of them too early. I should have shown you that. So thank you for asking. So what's going to happen here is we're just going to evaluate this thing. We're going to get 16/4. In the second bracket, we're going to get 1/4, okay? And as Hayoon told us, the c's are going to cancel each other out. So we're going to be left with a single number here, 15/4, okay? Which is the value of this integral. Okay. Now, a notation that often gets used when we're doing these things is, if I extend the page here, rather than writing out this subtraction step in here, I'll just do this in blue down here. What we often say is that the integral from a to b of f of x dx is equal to sort of the antiderivative, and then we use this vertical line here, which means it's evaluated at the endpoints. Okay. So basically when you see this, f at x with the vertical line and then a and b, this means f at b minus f at a is what that means. Okay. So it's a kind of a way of combining this stuff that I did over here with this stuff in here. Okay, so let's do another one here. Integral from pi to 2 pi of sine x dx. Okay. What is our antiderivative first? Yeah, cos x. Now, we should check by, in our heads, doing the derivative of this. What is the derivative of cos x? Negative sine x. We want to get a positive sine x, so what do we need to add out front here? A negative sign, yeah. So it's actually negative cos x. And what we want to do is we want to evaluate this from pi to 2 pi. Okay. So what does this really mean? It means negative cos x at pi minus negative cos x evaluated at 2 pi. All right, so what is cos at pi? It is, what is it? Is it 0? No, I don't think it is. I think it's negative 1. Is it negative 1? Yeah, negative 1. So we get negative 1 minus negative cos at 2 pi. 2 pi, it's back up to 1 again. So this is minus negative 1. So we get minus negative 1 minus negative 1, which is 2. Or is it 2 or is it 0? I don't know. Let's work this out. This is 1 plus 1. There we go. Equals 2. Yeah. For some reason I have negative 2 in here. That's a little bit weird. Okay. Anyhow, let's keep going here. Okay. So some general tips here to evaluate integrals. I said here that you need to know the differentiation formula backwards and forwards because, well, if you know them backwards, they're antiderivative formulas. Okay? All of your basic differentiation rules kind of still apply when we are doing integration. So what I mean by that is things like the constant rule. So if we are doing the integral of a constant times some function, okay, that is actually equal to the constant times the integral of the function, kind of like the way it worked with differentiation. Okay. We can have sum and difference formulas in here. Let's see, if you're doing the integral of two functions, f at x plus g at x, okay, you can, of course, break that into two separate integrals. The integral of f at x dx plus the integral of g at x d at x. Okay. Now, there are two types of integrals. There's what's called a definite integral and what's called an indefinite integral. Okay? The definite integral is what we looked at on the previous page, where you're given these two values for your endpoints. So you're integrating from a to b of some function. When you do a definite integral, your answer is always going to be a specific number. An indefinite integral is kind of what we were doing before when we were doing just straight antiderivatives. They don't give us the endpoints that we were supposed to evaluate this thing at. So we can't actually evaluate the integral. All we can do is come up with our antiderivative Okay. And add our constant onto the end here. Okay, so we end up with this kind of a family of functions, or a series of general solutions. Okay. So in addition to this stuff, there's basically this whole list of integration formulas that you need to know and a number of integration rules. I think those are all summarized in the learning guide or in the textbook. So it's something that you're just, as you're working your way through the practice questions, you should kind of refer to until you kind of know them. All right. So we'll finish off here. We'll just do a few more examples of some integrals here. Okay. So example 3 here, we've got the integral of 6x squared plus 5 cosecant squared x dx. So we're integrating this function here over x, but again, this is an indefinite integral. Okay, we don't have any endpoints. So our answer is just going to be a function with that constant c added onto the end. So if you had to do this integral, what would you think of doing first? What do you think, Daphne? Yeah. That's what I would do too. I would sort of break it up into two separate integrals. Okay, and for this cosecant one, I would actually probably pull the 5 out in front as well. So we're integrating cosecant squared x dx. Okay. And then I would attack each of these two integrals here. So I think the first one here, we can probably figure out how to do this. What would be the sort of basically the antiderivative of 6x squared? What do you think, Lee? 2x cubed? Yeah. Yep, because if we take the derivative of that, sure, we get that. Now, what about the antiderivative of cosecant squared? It is not tan x, I don't think. It's not tan, but it's cotan. And in order to get a positive, we need, because the derivative of cotangent is going to be negative cosecant squared, we need a negative sign out front to change it. So, and because this is an indefinite integral, we need our integration constant c on the end there. And then, I mean, all we can do here is clean this up a bit. 5 cotangent x plus c. All right, let's take a look at the next one here. We've got the integral from 1 to 8 of 1 over cube root of x squared dx. If you're doing this one, well, what would you think to do first? What did we do in differentiation when we saw something like this? How did we rewrite it, Daphne? Yeah, so write this as the integral from 1 to 8 of x to the negative 2 over 3 dx. Now, what is our antiderivative going to be in here? What do we think? It's a power law one, so we know that if we were doing the derivative, we would subtract 1 from the exponent. So we know that doing the antiderivative, we're going to have to add 1 to this exponent. So let's see, if we have negative 2/3 plus 1, we're going to have x to the 1/3 in here. Now, we need some way of canceling out. I mean, if we do the derivative of this, we're going to bring down the 1/3. We don't want a coefficient out in front here. So what do we have to do here, Daphne? And multiply by 3. And then, because this is a definite integral, we want to evaluate this from 1 to 8. So let's go ahead and do that. Give ourselves a bit more room here. Okay. We're going to have 3. Let's see. Sorry. 8 to the 1/3 minus 3 times 1 to the 1/3. Okay, what is 8 to the 1/3? Cube root of 8 is, Daphne, 2. So we're going to have 3 times 2 here, which is 6 minus 3. So this evaluates to 3. Okay, definite integral, our answer is always a single number at the end. Okay. Integral from 1 to 4 of t squared plus root t minus 2 over t dt. Any thoughts on how we would approach this? Imagine the poor student watching this video later, and they've just been subjected to 20 seconds of silence. They're like, just give me the answer. No. Okay, so what I would do first here is same thing that we did in the previous one. I'm going to try rewriting this to make it a little bit easier to maybe process here. So I'm going to rewrite this as the integral from 1 to 4. I've got t squared. My first term here is t squared over t. So that's going to cancel and just give me a single t. I'm going to think of this root t as t to the 1/2. If I divide it by t, I'm going to have t to the negative 1/2. And then this last term here, I'm going to rewrite it as negative 2 over t. And I do this because I can now think of this integration term by term by term. So, oh, sorry. Let's just do our antiderivative here. So, first term, antiderivative of t is going to be what? Here. 1/2 t squared. All right. Antiderivative of t to the negative 1/2. Well, let's see. We know that we're going to have something like t to the 1/2, because when we subtract 1, we're going to get t to the negative 1/2. We need to cancel out that 2, that 1/2 that we're going to get there. So let's put a 2 down there. Okay. So that's going to be plus 2t to the 1/2. What about this third term here? 2 times 2 over t. Think about it as 2 times 1 over t. What function, when you take the derivative, gives us 1 over something? That is our ln function. Yeah. So we need negative 2 ln t. Sorry? Maybe that's what it should be. Let's see, t squared. Let's double check that. If we do ln of t squared, and we do our derivative, what's going to happen here? We're going to get 1 over t squared times 2t. Yeah, that would work too, wouldn't it? 2 times ln t. Interesting. Is it going to matter which one we choose? Yes, oh, turns out it's not going to matter when we evaluate it. Phew. Okay. So I'm going to stick with 2 times ln t, and we're going to evaluate this from 1 to 4. Okay. All right. So evaluating this, let's see. Let's evaluate this whole thing first at 4. 4 squared is going to be 16, divided by 2 is going to be 8. 4 to the 1/2 is going to be 2 times 2 is going to give me 4. And then 2 ln t is going to give me negative 2 ln 4. And then I'm going to subtract from that this whole thing evaluated at 1. So that's going to be 1/2 plus 2 minus 2 ln 1. But of course, ln 1 is just 0. So we work all this out, doing this addition and subtraction, and we get 9.5 minus 2 ln 4. As our final answer here. And we could evaluate that if we wanted to. Okay. All right. Last example here. Doing the integral of sine 2x over sine x. Now, what do you think we might need to do with this one? What does the sine 2x suggest? Yeah, we need to use a trig identity probably to do this one. So what we're going to do is check our identity sheet, and we are going to change this into the integral of sine 2x is actually equal to 2 sine x cos x. This is still all divided by sine x, and we're integrating over dx. Okay. Now we can cancel out these 2 sine x's, and this becomes the integral of 2 cos x dx. So now we just need to integrate. The 2 is just a constant, so we know that that constant is going to come out front. We just need to integrate cosine x here. So what's the integral of cosine x? Sine x. Okay. This is an indefinite integral. We have no limits of integration here, so the best we can do is add our constant of integration and give a general function for our answer. Okay. And that's where we're going to stop.